So what we're going to attempt at this point is we're going to take the rate law, which we've already found connects the reaction rate to initial concentration. We're going to see if we can rearrange that a little bit to actually find the concentration as a function of the amount of time that's passed since a reaction has started. The way that we're going to do this is we're going to start, of course, with the rate law, which we already know connects the reaction rate, defined as the opposite of the change in concentration over the change in time, and connects that to the rate constant times the initial concentration taken to a certain order. And we, of course, already know that the most common reaction orders that we'll deal with respect to a certain reactant, is going to be 0th order, 1st order, and 2nd order. And we know that depending on what that order is, that changes what the reaction rate will look like. And so what we're going to do is we are going to have to consider each of the 3 different orders that are most common. We're going to see if we can find a way to re-express this so that concentration itself is expressed as a function of time, rather than the rate being expressed as a function of concentration. And here's how we're going to do that. We are going to take advantage of a little bit of calculus to think through this. If you're not already familiar with the calculus, that's fine. You won't need any calculus in order to use the results that we get, but it is helpful for showing where these equations come from. So here's what we're going to do. We are going to take advantage of the fact that we have a delta over a delta, and we are going to consider that to be an instantaneous rate of change. So we can go ahead and re-express that so that it's no longer delta over delta, but rather d over d, meaning this is now a derivative. It is the negative derivative of concentration with respect to time. And we can now find that based on the order of this reaction with respect to that reactant, we can find what the concentration will look like as time progresses. And we keep in mind that the only difference between the different rate laws for the different orders is simply what exponent each of these reactants is taken to. However, that's going to very significantly affect the way that this function itself plays out. Because as you're familiar with from your studies in calculus, different derivatives associate with different original functions. And the way that we're going to find those original functions is by taking away the derivative. Well, how do I take away a derivative? I integrate. And so what we're going to do, we're going to take each of these rate laws. We're going to first of all simplify them as much as we can. Then we're going to go ahead and we're going to integrate the rate law and see what we get for each individual reaction order. Let's start with the 0th order reaction, see what happens. We do right off the bat notice that since it's a 0th order reaction, that means that this concentration is taken to the 0 power. Well, if the concentration is taken to the 0 power, we already know that any number to the 0 power is just 1. But k times 1 is just k. We actually don't have to include the concentration to the 0 power here, which makes sense because our definition of a 0th order reaction was one in which the rate doesn't depend on the initial concentration. The rate is constant, regardless of what concentrations I'm actually dealing with. And so this is actually going to integrate pretty easily. We'll go ahead, in order to integrate this, we are going to separate the 2 variables that we are trying to run as a function. We are trying to find concentration as a function of time, so we will separate those variables, have concentration on one side, time on the other. Multiply both sides by dt. And then, while we're at it, we'll also go ahead and remove this negative to the other side because we're trying to find concentration as our dependent variable. So we're going to isolate that as best as we can. Move the negative to the other side. And as a result, we find 2 sides of this that will both integrate very easily. We'll go ahead and we will integrate this over a time interval. We're going to assume that the time interval starts at 0. It's an easy starting point. And we're going to run this until whenever we want to stop it. So we'll leave our upper bound of integration as just t, whatever time we stop this at. But we'll integrate both sides from 0 to t. And we know that the integral of dA is simply a, so the integral of d concentration is just concentration. So we can go ahead and we can simply write this as the concentration at time t minus the concentration at time 0, or the initial concentration, is equal to the negative factors out, the k factors out, the integral of dt is simply t. Well, that would be t minus 0. But minus 0 just cancels out. This ends up being simply negative kt. And we have found our change in concentration is simply equal to the negative of the rate constant times the amount of time that's passed, which again should make sense. The change here does not depend on any initial concentration or any concentrations at all. It's a 0th order reaction. So the change here is simply equal to the rate constant times how much time has passed. And that rate of change is equal to the rate constant. If I were to go ahead and differentiate this again, I would find that the rate of change of this is simply k. And that's what we had here. Contrast this with maybe our first order reaction. We try to integrate our first order reaction. Again, we'll do the same thing. We'll simplify this as best we can. We do note that we are taking concentration to the first power. Well, anything to the first power is just itself. So we don't really need that first power there, so we're just going to write that as the concentration. And from there, we'll do exactly what we did before. Separate our variables, but keep in mind, we need to get all of our concentrations together. So we're going to multiply by dt to get t over here, and divide by concentration to get concentration back over here. And we end up with negative d concentration over concentration is equal to k dt. And then, just like before, we'll go ahead and we'll move that negative over as well. We've separated our variables. We'll go ahead and we'll integrate to get rid of those derivatives. We integrate both sides again from 0 to t. And our right side looks exactly as our right side did earlier, so it's going to pull down the same way. That ends up being just negative kt. Our left side, however, this is a little bit different than what we had before. You might not recognize what integral this is right away, but if we consider it off to the side for a second, instead of concentration, just picture it as the integral of dx over x. And if you're still not seeing what that is, break it apart. This is really the integral of 1 over x dx, which you'll recall from your calculus studies, the integral of 1 over x dx is simply the natural log of x. Well, therefore, I can go ahead and I can complete this integration. I find out that is the natural log of the final concentration minus the natural log of the initial concentration. And again, I have found something that relates my change in concentration to the amount of time that's passed. However, since this is now a first order reaction, there's now going to be a natural log involved. The rate constant times the time is now going to give me the change in natural log of concentration, not concentration itself like it did for the 0th order. What about our second order? See how second order will work. Again, we will simplify this as best we can, but there's really not anything I can do to simplify this one. So I'm just going to leave it as it is, but I am going to make sure that I separate my variables. Again, move dt over to the right side, move concentration back to the left side. And again, I'll go ahead and I'll move my negative over. And then I go ahead and integrate. Just like before, my right side will integrate just as it did before. My left side, I will integrate, however, again, this is a different function, so it's going to run a little bit differently. So we'll go ahead and we'll start with the right side, because we've already seen what's going to happen there. That just becomes negative kt. Left side, I don't necessarily recognize that right away, but again, I can compare it to something I might already know. This is really the integral of dx over x squared. And again, if you don't recognize what that is, separate it out. This is the integral of 1 over x squared dx. Well, if I want to know what that is, I'll go ahead and I'll use my power rule for integration. Move the power up 1. Keep in mind this is actually x to the negative 2. My power is now x to the negative 1, so that becomes 1 over x, but I multiply everything by that new power I just got, which is negative 1. The integral of this left-hand side is negative 1 over the final concentration minus negative 1 over the initial concentration. And notice on this side, you've got a factor of a negative on both sides of the equation. We can go ahead and cancel that out. And again, we have found a way to relate the change in concentration to the amount of time that has passed. A few things to note: these three orders only work for the order that they are written for. I can only use this equation if the reaction in question is 0th order with respect to this reactant. I can only use this equation if the reaction in question is 1st order with the reactant that we're worried about. And likewise, I can only use this one if the reaction is 2nd order with respect to that reactant. I don't want to mix up these equations. I want to make sure I remember which one is which. And then also keep in mind, your 1st order and your 0th order both had a negative kt on the right side. 2nd order has a positive kt on the right side. Don't get those confused. But we can take these three different equations. They all came from the rate law. They were all the product of integration of the rate law. And therefore, we take all three of these together. We refer to these as the integrated rate law. And I can use the integrated rate law to directly connect the concentration of a reactant to the amount of time that has passed since a reaction has started, based solely on the rate constant and whatever other functions might be needed to relate those two. And this is going to be very helpful for predicting how much of a concentration is going to be left, how much of a certain reactant is going to be left, and by extension, how many products have been created. So we can use some stoichiometry for that after a certain amount of time has passed, and it gives us an idea of how we can really predict how much of a product is going to be made or how much of a reactant is consumed as time passes during the course of a reaction.